this is the user interface for the program. On the left hand side, LEDs show if the microphone detects an input, and that way you know if it's detecting the notes that you're playing. Over on the right hand side we see the tank function, which allows us to graph the notes that are detected by the microphone. So if a note's too sharp, then the green bar will fill up towards the top, and if it's too flat, it will fill up towards the bottom. And you can choose the string number from each string that you want to choose. On the right of it we see a number, and this displays the frequency difference between the desired frequency and the current frequency. The current frequency is also shown above with the closest string displayed above that. So when we look at how the system's laid out, we see that the audio input is assigned on the top left here. This section opens the reference to the audio input and allows us to manipulate it. This is achieved by passing it into an array and then turn it into a 1000 by 1 array at a time. We then use the detect peaks function to assign a number of LEDs on the myRIO to the audio input. So a louder audio input causes multiple LEDs to light up. The range is determined over here, so we see that the range is split over all 4 LEDs.
Okay, so once the signal has been broken up into various samples, it's diverted down here to an extract single tone information module. So this detects the frequency, or the dominant frequency most prevalent in the array, and put it into it, and this will be the input frequency used throughout the rest of the program. So we scroll down here, this is multiplied by 1000 to put it into the hertz, as it is by default in kilohertz. To condition the signal, we use a range of boundary values associated with each individual string. So this array here is made up of 6 numbers, 1 for each string, and these numbers are in kilohertz values of frequency slightly below that expected from the particular string. So this is low E, A, D, G, B, and high E. These values are all multiplied by 1000 to turn them into hertz, placed into this array. The string number selected by the user is assigned here, and a 1 is subtracted by it to turn it into a valid index number, so it is in the range of 0 to 5. This index number comes along here and selects the boundary value which is appropriate for that string. It's then brought along this wire, and a plus 35 is applied to it to create an upper limit. These are both put into a Butterworth filter in order with a sampling frequency of 1000. This is to make the signal more smooth and provide better end results. This is then taken up and applied into the next section.
So in the next section we want to generate an output for our graph to show us how sharp or how flat each of the notes are. This is done by taking the ideal values on the left hand side and subtracting the values that are detected through the microphone. The values that are detected through the microphone have to, the lower strings have to have a factor of 2 taken out, and this is because of harmonics in the strings. This is achieved by passing it through an array and dividing by the factor of 2 over here. The output is the difference between the ideal frequencies and the calculated frequency, and this is shown on the bar graph between a range of plus and minus 20 Hz from the ideal value.
So the audio signal in the recorded frequency post conditioning is taken and brought down to this for loop here. Now this section of the program is used to determine the closest note to the one being played. So the input frequency is brought here and brought to a for loop which has a maximum of 6 iterations. The for loop is compared to one of 6 values associated with each string. These are upper boundary values. So this is, for example, is the boundary value between the low E string and the A string, between A and D, D and G, and so on. Each of these values is multiplied by 1,000 to exchange it from kilohertz into hertz, and put in a greater than comparison with the input frequency. These are cycled through using the iteration counter for the for loop. If the input frequency is greater than the boundary value for one particular string, it passes out a true value, which is converted into 1, which is added on to a base 0 constant into a shift register. This is stored up to 6 times and added together. The idea is that the final output from this shift register will be a value of 0 to 5, depending on how many of these boundary values the input frequency is greater than. i.e., if you're playing the high E string, it should be between 0.287 kilohertz and 0.5 kilohertz. So you'll pass out a value of 1, 2, 3, 4, 5 times, and your output will be 5. Likewise, if your value is low E string, it will not be greater than a single one of these array values, and your output will be 0. So the output of this for loop is used as an index for this array of strings. And these are the individual string names going in order from lowest frequency to highest frequency. Thus, if you are playing the lowest note and indeed pass out a value of 0 from this for loop, it will be used as index 0 from this array, and you'll be able to output the value of E to the user. Likewise for each of the string names, and you should be able to accurately see the closest note value to the note being played.
So here you can choose your string number, and then it will show you in the graph how your string tuning's going, and it will show you the closest frequency which relates to all the different strings.
Okay, so I'll just